Assalamualaikum and hello everyone. My name is Sufi and today my teammate and I were going to walk you through a fascinating topic about the application of organic compounds in daily life. Let me start by asking, do you know what organic compounds are? Organic compounds are chemical substances that mainly contain carbon atom, usually bound with hydrogen and often with hydrogen, nitrogen, sulfur, phosphorus, or halogens like chlorine and fluorine. But why is carbon so special? Because carbon can form four bonds, allowing it to create a huge variety of complex molecules such as carbohydrate, proteins, lipid, and DNA, all essential to life. Now, let's explore why organic compounds are so important in our daily life. First, it is essential for life process. Organic compounds like carbohydrate, proteins, lipid, and nucleic acid are the building blocks of life. They give us energy, support cells, function, and carry our genetic information. Second is medicine and healthcare. Modern medicine rely heavily on organic chemistry. Most drugs such as paracetamol, penicillin, and insulin are organic compounds. They help treat pain, infection, and chronic disease like diabetes. Thanks to organic chemistry, scientists can also develop new vaccine and treatment. Third, food and nutrition. Organic compounds make up most of the nutrition we consume, like vitamin, amino acid, fats, and sugar. They support growth, boost immunity, and keep us healthy. Even food additives like preservative and flavoring are organic. Fourth is fuels and energy. Most fuels are organic, like petrol, diesel, kerosene, and methane are hydrocarbons that power our home, vehicle, and industry. Even renewable fuels like ethanol and biodiesel are organic, offering eco-friendly alternative for the future. Number 5 is industrial and construction material. Organic compounds are used in making plastic paint, adhesive, rubber, and more. These materials are vital in construction, packaging, electronic, and many other industries. Without them, modern infrastructure will not exist. Last but not least, number 6, household and personal products. Everyday products like soap, detergent, perfume, and disinfect contain organic compounds. They help us stay clean, smell good, and fight bacteria. Organic compounds improve our hygiene and overall quality of life. So guys, throughout this presentation, we'll cover the following key areas. First, the organic compound in daily life. Second, the polymer and materials. Third is the aromatic compound in medicine. And lastly, biofuels and sustainability. Each section will show how organic compounds shape the world around us.
Have you ever wondered how chemistry influences our daily lives? Organic compounds, or carbon-based molecules, all around us, shaping the food we eat, the product we use, and even the medicine that keep us healthy. In this section, I will explore some of the most important applications of organic compounds in our everyday routine. One of the most fascinating uses of organic compounds is in food and flavoring. Take ester, for example. They are responsible for fruity scents and flavor. A common one is isomyl acetate, which gives banana the distinct aroma. In addition to flavor, organic compounds play a crucial role in food preservation. Benzoic acid, found in many packaged foods, help prevent spoilage and extend shelf life, making food safer to consume. Next, let's talk about something we use every day. Cleaning products. The reason soap and detergent effectively remove grease is due to organic compounds called surfactants. These molecules have a unique structure. One part attracts water and the other attracts oil. This allows water to wash away dirt and grease. A common surfactant, sodium lauryl sulfate, is found in shampoos and soaps, helping them create foam while lifting impurities from surfaces. Organic compounds also play a key role in healthcare. One famous example is aspirin, or acetylsalicylic acid, which helps relieve pain and inflammation. What makes organic compounds so interesting is how small molecular modification can completely change a drug's function. Understanding these chemical properties allows scientists to design new medicine with improved side effects and fewer side effects. Finally, let's talk about materials, specifically plastic. Organic compounds called polymers make up synthetic materials like polyethylene, which is widely used in packaging and textiles. Polymers are strong and flexible, making them ideal for various applications. However, plastic waste has led researchers to develop biodegradable polymers, which can naturally break down, reducing environmental impact. Basically, organic compounds are everywhere, whether it's the food we eat, the product we use, or the medicines we rely on. Their unique chemical properties allow us to improve technology, health, and sustainability. In the next section, we will dive deeper into how polymers, one of the most versatile types of organic compounds, shape modern materials. Let's go!
Hello everyone, today we're diving into the fascinating world of polymer and material. Let's begin by understanding what they are. Polymer are large molecules made up of many small repeating units called monomer. These monomer bond together in long chain. Natural polymer include DNA, protein, rubber, and cellulose. Synthetic polymer are man-made like plastic, nylon, and polyester. Polymer are used in everyday items such as plastic, bottle, clothing, packaging, and medical device. Material are substance or mixture used to make things. They can categorize into metal like iron and aluminium, ceramic like glass and pottery, polymer like plastic and rubber, composite mixture like fiberglass. These materials are essential in construction, electronic, transportation, and clothing. Now let's explore how polymers are used in real-world application. Well, look at three key areas: packaging, textile, and biodegradable plastic. Packaging. Used in bottle, wrapper, container, polymer, PE, PP, PET. Feature lightweight, flexible, and moisture resistant. These properties make polymer ideal for protecting and preserving product. Textile. Used in clothes, sportswear, robes, polymer, nylon, polyester, acrylic. Feature strong, elastic, wrinkle resistant. Polymer help create durable and comfortable fabric for everyday and athlete use. Biodegradable plastic used in compostable bag, cup, medical item. Polymer PLA, PHA, stretch base. Polymer break down naturally, eco-friendly. These are sustainable alternatives to traditional plastic, helping reduce environment impact. To understand how polymers are made, let's look at polymerization, the process where monomer join to form polymer. Addition polymerization. How it works: monomer add together without losing atom, common in alkenes. Need a catalyst and initiator. Example, ethane, polyethylene. This method is used to make plastic like polyethylene, common found in packaging. Condensed polymerization. How it works: monomer join and release small molecule. For example, water involve monomer with two functional group. Example, dicarboxylic acid plus diol, polyester plus water, dicarboxylic acid, diamine, nylon plus water. This method is used to create strong, durable polymer like nylon and polyester. In summary, polymer and material are all around us, from the clothes to wear to the packaging we use. Understanding how they're made and applied help us innovate for a better, more sustainable future.
Now we are moving to the aromatic compound in medicines. Aromatic compounds, particularly benzene derivative, play a pivotal role in a modern pharmaceutical due to their structural versatility and molecular interaction capability. Over 60% of FDA-approved small molecule drugs contain aromatic rings, including widely used medications like aspirin and paracetamol. So, why aromatic compounds are effective in medicines? First of all, it is because of structural stability. During it, planar benzene ring provide a stable scaffold for drugs molecules, enabling precise interaction with biological targets like enzymes or receptors. Second, it is because of molecular interactions. Aromatic ring engage in electron interaction with aromatic amino acid in protein like thyroxines. It is because to enhancing binding affinity. So, hydrophobic effect. Benzene lipophilicity its membrane penetration and bioavailability. Hydrogen bonding is functional group attached to aromatic rings such as hydroxyl from hydrogen bonds with target improving specificity. Last but not least is tunability. Substituent on benzene rings such as OH and CH3 can be modified to optimize pharmacokinetic, reduce toxicity, or enhance metabolic stability. So, there are one case study which is aspirin development. Aspirin evolution from salicylic acid, which is a natural compound in a willow bark, exemplifies strategic aromatic modification such as original compound. Salicylic acid, which is anti-inflammatory but causes severe gastrointestinal irritations. Second is aromatic modification. Acetylation of the hydroxyl group OH on the benzene ring produce acetylsalicylic acid, aspirin, which reduce gastric toxicity by limiting direct acid exposure, maintain anti-inflammatory and analgesic property through target cyclooxygenase (COX) inhibition. Third one is impact. Aspirin became a cornerstone drug of pain relief, cardiovascular protection, and anti-inflammatory therapy. Next, we move to the modern application, which is targeted drug design. First is imatinib. These leukemia drugs further a benzene ring modified with a methyl group and pepperizing substituent, enabling selective inhibition of the BCR and ABL tyrosine kinase. Selakabic, a COX2 inhibitor with a sulfonamide substitute benzene ring, designed to minimize gastrointestinal side effects. Challenges and innovation. While aromatic compounds offer therapeutic advantages, their metabolic instability, such as hydrolysis of aspirin to salicylic acid, and potential toxicity, like benzene contamination in excipients, drive ongoing research into bioisoteres, like replacing benzene with heteroaromatic rings like pyridine to improve safety. Metabolic shielding, editing fluorine or metal group to block enzymatic degradations. Aromatic compounds remain indispensable in drugs discovery, balancing efficiency, stability, and safety through precise molecular engineering.
Biofuels and sustainability. What are biofuels? Biofuels are renewable fuels made from biological materials like plants, algae, or animal fats. Common type includes biodiesel and bioethanol. Benefit: renewable impact is made from crop or waste, can be regrown or refused. Lower emission, reduce CO2, sulfur, and particular emission versus fossil fuels. Biodegradable, safer for the environment in case or spill. Support circular economy, use waste oil and non-food crops. Example, biodiesel's production is made from vegetable oil or animal fat. Process, transesterification, produce biodiesel, FAMES plus glycerol. Next is fossil fuels versus biodiesel. Organic compound compare. The first one is aspect source. Fossil fuels decompose at sin or organisms millions of years old. Biodiesel, renewable plant oils or animal fat. Type of compounds, hydrocarbons, alkane, cycloalkanes, aromatic compounds, fatty acid methyl ester. And number three is chemical structure, mostly nonpolar carbon hydrogen chains, polar ester with long fatty acid chain, combustion emission, high CO2, sulfur oxidize, nitrogen oxidize, lower CO2, minimal sulfur, biodegradable byproducts, renewability, non-renewable, finite, renewable, sustainable. Environmental impact, high population, greenhouse gases, lower emission, better biodegradability. Okay. And next is transfer esterification in biodiesel production. Definition: transfer esterification is a chemical reaction that convert oil or fat triglycerides into biodiesel fatty acid methyl ester PAMs using an alcohol and a catalyst. Process step is feedstock, vegetable or oil, animal fat, triglycerides. Alcohol, usually methanol or ethanol. Catalyst, base sodium hydroxide now or potassium hydroxide co. Acids, sulfuric acid H2SO4 for high free fatty acid content. Reaction condition: moderate heat 16 degree. Stirring for 1 or 2 hours. Products form biodiesel fumes, fuel used in diesel engine. Glycerol byproduct used in soap, cosmetic and pharmaceutical. Pharmaceutical. Reaction formula is triglyceride triglyceride plus alcohol, example methanol, and then glycerol plus fatty acid methyl ester, biodiesel. Future of organic compounds in green energy. Overview: organic compounds, carbon-based molecules from renewable sources are playing an increasing role in clean, sustainable energy technology. Sustainability benefit: renewable and biodegradable, lower carbon footprint, support circular economy by using waste material, reduce reliance on fossil resource. Advanced biofuels, second and third generation biofuels from algae, crop waste, and non-edible plant. Example, cellulosic ethanol, biobutanol, less competition with food supply. Organic photovoltaic, OPV, solar cell made with organic semiconductors. Lightweight, flexible and cheaper than silicon-based panel. Ideal for portable or wearable solar tech. Green hydrogen from biomass, organic matter like crop residues used to produce hydrogen via gasification. Potential zero emission fuels source. Bio-based batteries. Use of organic redox compounds in flow batteries, eco-friendly energy storage with lower toxicity.
In conclusion, organic compounds are the foundation of life, the backbone of the modern civilization. They are found in food, clothing, medicine, energy, and technology, playing a role in nearly every part of our life. Organic chemistry not only help us understand life at a molecular level, but also help us solve real-world problems from developing eco-friendly product to creating sustainable energy solution. By recognizing their importance and using them wisely, we can build a healthier, greener, and more advanced future. So this is the end of our presentation. I hope this presentation help you understand more about chemical organic in your daily life. Thank you.